Okay, so say that I have a function that goes from R to R, and what it does is it takes x and it maps it to the sine of x. If this is the case, first off, are you familiar with this notation that I'm using? Yeah? Cool. So if this is the case, what is the domain of f? R, right? So the domain is the set of all things that you could input into the function, and it's always going to be this, right? It's always going to be the first set. So then I'm going to ask, what's the codomain of f, and what's the range of f? This one's a little tricky. The codomain, like the difference between codomain and range, people often get confused. In this case, the codomain is R, and the range is the interval -1 to 1. So they're different. The codomain is always what you have here. The range is the set of things that this function can reach, right? Sine of x only goes between -1 and +1. Now, maybe you're asking, like, why didn't we just put -1 to +1 here, and then that would be our range and our codomain? I mean, you could, is I guess the long and the short of it. But think about like a lot of your computer scientists, think about like if you were writing a function in like Python, or maybe Python's a bad example. You're writing a function in like Java or C++ or something, right? You have to declare the type going into the function and the type coming out of the function, right? So maybe you have a function, I don't know, I was trying to think of an example and I didn't do very well, but say you have a function that's uses AI. You take a picture of your work and it gives you, I don't know, like a number grade, like, you know how in high school they have like 1, 2, 3, 4 for your grades or whatever. So it takes a picture of your work and gives you a 1, 2, 3, or 4. You would probably use an int data type for that, right? Like an integer. But that grade that it spits out couldn't be, 500, right? It has to be between 1 and 4. So that's the difference between range and codomain. It's like, what is the type of the output versus what can it actually output, right? What can that function actually output? Does that make sense? Cool. Okay, so that was a little bit of function theory, I guess. And we'll talk about this in the context of linear algebra. So I'm going to throw out a few words here. So function, I think most people are familiar with functions. But a concept of a map, a transform, and an operator. Does anyone know the differences between those? Guesses? Yep.
Well, I guess for operator would be just like a function that is just one operator, like addition, subtraction, multiplication, division, and like square root or something.
Yeah. That's a specific kind of operator. We have a more general notion of it though. What you're talking about is called a binary operator because it takes two things. Binary, but yeah, there's sort of a more general idea. So a function, so I'll start off by saying a function and a transformation are the same thing. Those two words are completely interchangeable. A map, so remember in high school when you were doing like functions and stuff, they had like this whole vertical line test, right? So they said like if you can draw a line through your curve and it hits at multiple points, then it's not a function. That's true. So that is like a requirement for something to be a function, right? But then the question arises, what is it if it's not a function? It's a map. Does that make sense? Maps are, like all functions are also maps. It's just a map is a function that doesn't have that requirement, right? Doesn't have that specific vertical line requirement. So like, for example, you could have like a map, I'll call it F, that if you plug in 0, it could give you 3, and maybe if you plug in 0, it could give you 5, right? Maybe it's like a random variable or something, right? I don't know. But in a sense, it's not like reproducible, right? And then an operator is a specific kind of function. An operator is a function whose domain and range are equal. So whenever I shouldn't say that. Whose domain is equal to its codomain. So in this case, this function is an operator because it takes something in R and it spits something out in R. It doesn't matter what the range is, it's just sort of how you define it, right? We're going to talk about transformations. We'll usually use the letter T, and if they go from one vector space to itself, then we call it an operator. Does that make sense? Whereas if it was from V to like W or something, then it would not be an operator. Does that make sense? All right. So I'm going to talk about a specific kind of operator. Not operator, transform. Called a linear transformation. So the key piece there is linear. We like to do this sort of game in math where so we're going to start by talking about linear transformations. And we do this sort of thing in a lot of cases. So someone asks you, what's a linear transformation? The definition is that it's a transformation that's linear. It's like, well, that didn't help me at all, right? What does it mean for something to be linear, right? The answer to that is that it has to be additive and it has to be homogeneous. And if you go on Wikipedia, this is what you're going to see, right? It's like, well, what's a linear transformation? You can see it's a transformation that's linear. It says, well, what's linear? Well, it's additive and homogeneous. So it's almost like a rabbit hole, right? It's like, well, what's additive and what's homogeneous, right? So you can sort of keep going. And then at some point, it'll start talking crazy language to you and you'll give up. So at some point, you sort of have to like when we teach math, we don't teach it from the ground up. We sort of teach you like halfway through and just, cut it off at some point and say, this is what this is and this is what this is, and we'll stop. So that's what we're doing here. So additive, a function or a transform in this case is additive if it takes two things in and you add them together, you can separate them under that addition. Like that, right? Transform is homogeneous if you have like a scalar multiplication, if you can pull that scalar out. Does that make sense? So it's linear if it satisfies this property and it satisfies this property. Does that make sense? Yeah. So let's I'm trying to think of a good example. Well, let's think about an example of a function that is not linear. So what if I had a function, when I'm writing f here, maybe it's worth noting that I'm talking about a function that's going from like R1 to R1, right? So this is like a normal function. So what if I have a function that's, I should say a function that maps x to x squared. So it takes any real number and it just spits out the square of it. Well, that function, if we're asking, is that a linear function or is that a linear transformation? If I were to say f of x plus y, that's going to be x plus y squared, right? Which equals x squared plus y squared plus 2xy, right? You sort of use like the foiling, expanding stuff. If I consider the other side, if I have f of x plus f of y, that's just x squared plus y squared. So they're close, except this one has that extra 2xy, right? Which means it's not linear. They'd have to be the same. They're not the same, it's not linear. It's not additive, right? Now, this sort of, kind of, in a sense, is like the whole vector space stuff, in that like, you need to have both of them true, right? If one of them fails, then it's not linear. They both have to be true. So we've shown it's not additive, that means it's not linear, right? Okay, let's talk about transforms as, or matrices as transforms. So every matrix is also a transform. So say that I have, and maybe I'm going to draw these a little bolded to be our sort of main axes here. Like that. Say that I have like a grid, a set of grid lines here. I'm going to draw this out, so hopefully if I had like animation on the computer, it would probably be easier, but I'm not that good. So say we have like a set of sort of your normal standard grid lines here, and pretend that they're all nice and square and even, and you know. So, you know, you could sort of use those grid lines to get you like any vector, right? So like if I had a vector, maybe let's say that I have a vector that's like this, right? That vector, we're going over 1 and up 1. So that vector is like 1, 1, right? Okay, so what we can do is, obviously we sort of have two special vectors here, right? The two sort of key vectors that we're considering are like this vector, which I'm gonna call I hat, and this vector, which I'll call j hat. I hat being like 1, 0, and j hat being 0, 1. Does that make sense? So if we have a matrix, let's say I have the matrix 1, maybe I'll do 0, 1, minus 1, 2. Say I have that matrix. We can think of any matrix as a transformation, as a linear transformation. And this is why we call it linear algebra, is because of this idea that every matrix is actually a hidden linear transformation. The sort of rule that we use is that the transformation that's associated with A applied to any vector is equal to A times that vector. So you just do multiplication. So maybe a good thing we could do is figure out what that transformation applied to our standard basis is. So if we do, well, maybe I'll write it out. If we do this matrix A times I hat, which is 1, 0, what do we get? Anyone know? Not quite. Not 1, 0. So if we do 1 times 0 plus 0 times -1, we should get 0.
0.
Yeah. And then if we do 1 times 1 plus 2 times 0, we get 1. So T of I hat is 0, 1. Now if we look at T of J hat, it's going to equal our matrix A multiplied by 0, 1. And what do we get there?
Minus 1, 2.
Yep. -1 and 2. And literally, you can just like pull it out, right? Your answers are just the columns, always. Okay, so I'll draw them onto this grid, those new vectors. So I hat became just j hat, right? So just straight up. And then j hat became -1 and 2, so it became like this, right? And so I can sort of continue these grid lines, and maybe my drawing's not perfect, but that was not good at all. Something like that. I could continue this grid line, sort of just extend it. Those could be like a new set of axes. We've kind of like rotated, squished, done something crazy, right? And made almost a new set of grid lines. They're not at 90 degrees. Now they're kind of skewed like that, right? And stretched and all funky, but they are grid lines, right? So I could continue drawing more grids. So for this one, I can just keep drawing sort of the straight up and down. Markers running out, but hopefully you get the idea. And then for this diagonal one, I could go here and draw things like that, roughly. Drawing's not great. And then I guess like, trying to figure out where I would draw the next one. I think here? Here. Yeah? Is that right? I feel like it's not. No, it's right, yeah. My drawing's just not good. And I could draw one like here. And I don't know, draw one like here. Yeah. So we've got like a new set of grids, right? I've taken that old set of grids and I've like rotated it and sort of squished it, right? And made a new set of grids. New like sort of grid lines. So like in this new grid line, we could sort of think about like this point here. Maybe it's hard to see, I'll try and, these are like our grids coming out, right? We could think about that point there as being like sort of roughly one, how would I do that? I think it's -1, 1, right? So it's going back 1 and then up 1. You sort of see that? Okay. So really, what these grid lines tell you is that if I applied this transformation, which is the same as multiplying this matrix by any vector, it'll give me this new vector. So if I were to multiply this matrix by -1, 1, I would get this vector here. Maybe I should use pink because this green does not seem to be working. I would get that vector there. And that vector, if you translate it, like look at this pink vector in terms of where it lands with the pink grids, that would tell you the answer of that multiplication. So transformations and matrices are the same thing, right? Okay. So one more quick thing I want to do, assuming I have time. Just want to double check how I'm doing. Yeah, we're good. So let's say that I wanted, so in this example, I gave you a matrix, right? And we changed that matrix into a transformation and then played around with it. So we turned a matrix into a transformation. What if we want to go the other way? What if we want to go transformation to matrix? So what we would do, let's say that usually you'll be given something in words, right? So let's say that T is a transformation that rotates any vector 45 degrees counterclockwise, right? So it takes any vector and it just like rotates it a little bit. right? If we wanted to find the matrix for that, the matrix representation of that transformation, sometimes you'll hear that called like the standard matrix. So we want to find the standard matrix of T. What we would do is we would say, well, what happens if we apply T to I hat, right? What do we get? Any ideas? So if you rotate I hat, which is like, remember I hat is 0, 1, oh, sorry, 1, 0. What happens if you rotate that 45 degrees counterclockwise? Yep.
1/2, 1/2, 1/2.
Yep. So a lot of people initially would think 1, 1, right? If you take it and like rotate it 45 degrees. But the length of this is 1, and the length of this is square root of 2. So you've sort of, in writing this, you've like rotated but also stretched, right? So we kind of have to scale it back to make sure that the length of this thing is 1. So you get 1/√2, 1/√2. And then what about j hat? What happens if we take j hat, which remember is 0, 1, and we rotate it 45 degrees counterclockwise? So we're starting with like this, and we're ending up like there. Any guesses? Yeah.
Minus 1/√2.
Yep. So it's minus 1/√2, 1/√2. Cool. So we've written down the two, like what happens when you apply the transformation to each of your basis vectors. Even if this is in 3D, you just, use, like you do this 3 times, right? You do like 1, 0, 0, 0, 1, 0, 0, 0, 1, right? Get your results. And those results become the columns of your matrix. So you get 1/√2, 1/√2, minus 1/√2, 1/√2, like that. Does that make sense? Cool. And then that matrix, you could multiply anything by that matrix, any vector, and what it'll do is it'll rotate that vector by 45 degrees counterclockwise. Make sense? Cool. Okay, so I'm gonna stop there.